We have a second talk on the zero-hack algebra, this time on its action on the Stanley-Reisner ring of the Boolean algebra, and it's by Jia Huang. Please.
Thank you very much. Thank the organizers for giving me this opportunity to speak here, and also for arranging my talk right after Basu's talk on a related topic. So today I will be speaking on zero-hack algebra actions on Stanley-Reisner ring of the Boolean algebra. The plan is to first review symmetric group and the zero-hack algebra, and then review the actions on polynomials. And I will show you some results there, which motivates my study on the action on the Stanley-Reisner ring. And from this work, I can derive some results on non-commutative Pauli-Hooke symmetric function and some generating functions on permutation statistics. So first, this is a well-known presentation for the symmetric group. It's generated by n-1 transpositions, Si, where Si permutes I and I plus 1 and fixes everything else. And then the relations satisfied by these generators are the following. You have Si squared equals 1, and then the usual braid relations for these generators. And the zero-hack algebra is a deformation of the symmetric group, or its group algebra really, because it has generators pi 1 through pi n minus 1, and the relations are very similar to the SIs. And you have pi I squared equals pi I. You saw this in Basu's talk. And then the same braid relations, okay, for the pi i's. So the only difference is this quadratic relation for pi I. So that's one definition for the zero-hack algebra. And then because they look pretty similar, okay, and I hope we can find some more evidence to support this analogy between the symmetric group and zero-hack algebra. So one place you can find more analogy is you can look at representation theory. So for Sn, the complex representations are semi-simple, which means you can always decompose them into the direct sums of irreducible modules or simple modules. And the simple modules are indexed by partitions of n. And you can send this to a short function indexed by the same partition, and that gives you a nice correspondence between representations of Sn and symmetric functions. And direct sum of representations corresponds to sum of functions, and then products of functions corresponds to the induction products of representations. So you have this nice correspondence, okay? And now I want to show you some analogous correspondence between representations of zero-hack algebra, okay, and some other functions. And to do that, I need to first review some notation. A composition of n, you saw this in Basu's talk also, is a sequence of positive integers whose sum is n. And there is no requirement for the ordering of these integers, not like partitions. And the descent set of this composition is the set of partial sums. And this is a bijection. If you have a composition of n, you take its descent set. You have some subset contained in the set 1 through n minus 1. This is bijection. And there's another bijection between compositions and the ribbon diagrams. Okay, I'm going to show you this example here. I take the composition alpha to be 2, 3, 1, 1. This is a composition of 7. The descent set consists of 2, 5, and 6. And you can also draw a ribbon diagram. You have the bottom row of length 2. The next row, it has length 3, and the next row has length 1, and then the last row has length 1. And you stack them one on top of the other, and you insist that this is connected, and also there is no 2 by 2 boxes. So there is only one way to do this. That gives you this bijection. Okay? And also we have these analogous half algebras to the half algebra of symmetric functions. Sim, the ring of symmetric functions, is a self-dual half algebra, and QSim and NSim, QSim is the half algebra of quasi-symmetric functions, and NSim is the half algebra of non-commutative symmetric functions. they are dual to each other. And also sim is included in QSIM, and NSIM has a surjection to sim. So you have this nice relation between these half algebras. And oh, this is what I said. And also there are nice bases for sim, as you know, the short bases. There are self-dual bases, and then there are these monomial bases and these complete homogeneous bases. They are dual to each other. And for QSIM and NSIM, we have also nice bases. For QSIM, there is a monomial basis, and also there is a fundamental basis, and they are dual to each other. And oh no, I'm wrong. Sorry. For NSIM, there are two bases, H and S, and then the duality between QSIM and NSIM is given by, sorry, it's a pointer, given by M and H. That's the duality between M and H, and also a duality between F and S. Okay. So now let me review the representation theory of the zero-hack algebra. It started by Norton in her thesis. So she decomposed the zero-hack algebra, the regular representation, into the direct sum of p alphas indexed by compositions of n. Okay? And each of these p alpha is indecomposable. And here is an example. If you have n equals 3, there are 4 compositions of 3. So you have 4 indecomposable representations of H30. Okay, and the direct sum of these is exactly the regular representation of H30. And because each of these p alphas is a direct summand of a free module, they are projective. Okay, so they are projective and indecomposable. And they are indexed by compositions, and they are pairwise non-isomorphic. And there are also simple Hn0 modules, and you can get this by just taking the quotients of the p alphas by the radical. And here the radical of p alpha is just the unique maximum submodule of p alpha. Okay, and it has to be simple because the thing you quotient by is maximum. And so these basically give you all the irreducible or simple Hn0 modules. Okay, and again indexed by compositions. So you can see some analogy between these and the representations of Sn. And there are these two characteristic maps introduced by Krop and Tikum. So for a p alpha, a projective indecomposable, you send this to a non-commutative Riemann short function indexed by the same composition alpha, and it's in NSIM. And if you have a simple module indexed by alpha, you send this to a fundamental quasi-symmetric function indexed by alpha, and it's in QSIM. Okay? So this gives you a nice correspondence between representations of Hn0 and functions in QSIM or NSIM. Okay? So questions so far? Okay. Now let's look at the action of Sn on polynomials in n variables x1 through xn. And of course this action is by permuting these variables. And for any partition mu of n, we can construct an ideal J mu in this polynomial ring, and that is stable under the action of Sn. And it's also homogeneous. So that means you can take the quotient, say that is R mu, and there's a nice interpretation of this, is isomorphic to the cohomology ring of the Schrödinger fiber, indexed by the same partition mu. Okay? And for our talk, we just need this to be Sn module. Okay? And an example of this is when mu is the partition 1, 1, 1, 1, 1. The ideal J mu is exactly the ideal generated by the elementary symmetric functions. And the quotient of ring R mu is a co-invariant algebra. Okay? And if your partition is in general, say let's say 2, 2, then the ideal is generated by these functions. You always have the elementary symmetric functions there, and you may also have some partial elementary symmetric functions. okay, in certain number of variables. There's a rule to tell which variables are there and then what are the subscripts of these EIs, but I'm not going to say that. Okay, just look at the partition, you can tell that. And the nice result is by Harter-Springer and also Garcia and Berchesi, the graded Frobenius characteristic of this ring R mu as an SM module is the modified Hollywood symmetric function. Okay? And the Hollywood symmetric function is very nice and arises in different areas. And this is an interpretation by representation theory. And this also proves the non-negativity of these coefficients, k, lambda, mu, t, the Kaskar-Fuchs polynomials. So that's a very nice result. And the special case of this is if you take mu to be the partition 1, 1, 1, 1, I said the ring R mu is the same as the co-invariant algebra. And then you look at this Hollywood, you find you actually have the regular representation of Sn. And this result is, of course, well known, and it was proved by Chevrolet in 1955. Okay? So these are very nice results about some Sn representations. And my goal is try to get some analogous representation of zero-hat algebras, and I hope to get some functions which are analogous to this Hollywood and which sits inside anything. Okay? So that means I need to consider actions of H10 on polynomials, and this is one way to define H10 action on polynomials. You use these Stanley-Reisner operators. You can, that's the formula. It's a quotient, but the result is always a polynomial. There is also another way to define this action. You can, if you have a monomial, you let pi I act on this monomial in this way. There are three cases depending on xi, the exponents of xi and x plus 1, which one is larger, which one is smaller, or they're equal. There are three cases, but you can tell this, okay? It's not so hard. And in 2011, I proved this result for the co-invariant algebra with this action of H10. It actually carries the regular representation of H10. So this gives an analogy to the result by Chevrolet. Okay? And I gave a talk on this result in FPSAC in Iceland 3 years ago. And if you remember, if you have seen that talk and remember anything from that talk, I guess it would be this picture, which shows my results from N is 3. So this picture on the left-hand side shows you the regular representation of H30, of course decomposed into indecomposables. And somehow you can use this ribbon tableau to model this representation. Okay? And there is a way to tell you how to let the H10 act on this tableau. Okay? And which is similar, in some sense, similar to the action you saw in Vasu's talk. Not exactly the same thing, but similar. And now this picture, on the right-hand side, shows you the co-invariant algebra on N is 3. And you have these monomials. Of course, you may recognize these are the descent monomials. And when N is bigger than 3, you may need polynomials whose leading terms are descent monomials. And then the action of H10 with, by the demonstrator operators matches with the action of H10 on this tableau. So that's how I prove they're the same thing, they're isomorphic. Okay? And you can also take the non-commutative characteristic for this co-invariant algebra. For each connected component, you look at the ribbon diagram, take the composition, and then you turn this to a non-commutative ribbon short function. And then you multiply by t to the degree of these monomials. And that's the graded characteristic, non-commutative characteristic for this H10 representation. So you can get some non-commutative symmetric function from the co-invariant algebra as an H10 module. And that solves the problem, the question I asked when mu is 1, 1, 1, 1, 1. So I had an analogous result for this for the case where mu is 1, 1, 1, 1. And of course, I want to go forward, and so I hope I can do this for all compositions. And first of all, we do have some analogous function in NCM to the Hollywood. There are actually few versions, different versions of non-commutative Hollywood. And this one was introduced by Nantel Bergeron and Mike Bronchi. And that's the definition. And you have a sum of non-commutative Riemann-Shor functions. The coefficients are t to the match of this indexing composition. And the match of a composition is the sum of the descents. Okay? And so they also had a QT analog, okay, using some kind of Nabla operator, Q Nabla operator. So that's from their work about 10 years ago. So that's something I try to interpret, okay, using representation of H10. So first of all, at first I wanted to still use this ring R mu, a quotient ring of the polynomial ring by some ideal. But I realized this only works when the composition alpha is a hook. Okay. So what happens if alpha is not a hook? In that case, I need the Stanley-Reisner ring of the Boolean algebra. That's why I consider the action on this object. Okay. So let me first tell you my results when alpha is a hook. So this ideal J mu, if mu is a hook, then it is stable under the H10 action. So that means this ring R mu becomes a module, a representation over H10. And you can consider its characteristic and it's projective, so it decomposes into those P alphas. And if you take the non-commutative characteristic and throw in the gradient, you have exactly this non-commutative Hollywood indexed by these hooks. Okay. And moreover, if you take the quasi-symmetric characteristic, you have some function in QSIM, but in this case, it's actually symmetric. It's not only quasi-symmetric, it's symmetric. And it's the same Hollywood you have when mu is a hook. Okay. So when the indexing object is a hook, then the result is, as nice as possible, right? So what happens if alpha is not a hook? Well, I need to use the Stanley-Reisner ring of the Boolean algebra, but maybe you have some other idea. Okay, I'd like to hear that, if you have any idea on this. But let me tell you my results. Okay, so I consider first the Boolean algebra is the rank coset consisting of all subsets of the set 1 through n, and the rank is by the cardinality of these sets, and the order relation is by containment. And this is an example when A is 3. You have this nice cube. And I will use the multi-chains in this coset. This is an example of a multi-chain. You have a chain of subsets, one contained in the other, another, and then you can repeat some set for as many times as you want. Okay? So that's why you call this a multi-chain. And the shorthand notation for this is you write down a permutation and then add some vertical bars between these numbers, like this. And that means you first have a set consists of 2, and then you throw in a 1, so you have 2, 1, 2, and then you have 2 bars there. That means you repeat this set 1, 2 twice, and then you finally have the set 1, 2, 3. Okay. So, and the rank or the rank of this multi-chain is going to be 1, 2, 2, and 3, right? 1, 2, 2, 3. Just read off the cardinalities. And I'm going to need this, okay, when I study the Stanley-Reisner ring of the Boolean algebra, which is defined as the quotients of the polynomial algebra in the variables y sub a, where a runs through all subsets of the set 1 through n, and you take the quotient of this by the ideal generated by the products ya times yb, where a and b are incomparable subsets of in the Boolean algebra. Okay, so if you have two elements in the Boolean algebra that are incomparable, the product of the corresponding variables should be 0. And that means if you have a monomial, if you have a product of these variables in the Stanley-Reisner ring, the only time you have this thing not equal to 0 is when these indexing sets A1 through AK, they form a multi-chain. They are pairwise comparable. Okay, that's why I need multi-chains. And these multi-chains actually index a basis for the Stanley-Reisner ring. Okay, given a multi-chain, convert this to a monomial, and you got a basis. Questions so far? Okay, so and also you have a multi-grading, right, of this for this Stanley-Reisner ring, just taking the rank multisets of the multi-chains. And the example is this. You have this multi-chain, we just saw this a minute ago, and we have this monomial corresponding to this, y2 times y12 squared times y123. Question?
So is that the same thing as the Stanley-Reisner ring of the arithmetic division of the simplex?
Yeah.
Okay.
Okay, so I use this variables t sub I to denote this multigrading, and you have ti to the multiplicity to the multiplicity of this in the rank multiset. And so now I have the Stanley-Reisner ring. I know a basis, and I have a multigrading for this ring. Okay. And you may think at first this ring is a little strange or not so standard, but actually there's a nice relation between this ring and the polynomial ring. You can do this transfer. Okay, you can given a multi-chain, and then you have this variable, this monomial indexed by this multi-chain in the Stanley-Reisner ring. You transfer this to a monomial in the usual polynomial ring, and you convert a variable y, say y sub 1, 2, you would transfer this guy to x1 times x2. Okay? And so for this guy, you have x1 times x1, x2 squared times x1, x2, x3. That's how we do the transfer. And if you apply this transfer map to the Stanley-Reisner ring of the Boolean algebra, you have almost a vector space isomorphism. You just need to get rid of the empty set. And this is actually not a ring homomorphism. So if you have, say, this product, y1 times y2, and the singleton set 1 and 2, they are incomparable. So the product should be 0. But if you transfer these two sets to the polynomial ring, you have x1 and x2, the product is not 0. So this is not a ring homomorphism, which makes this more interesting. Okay? So now, I'm going to consider actions of Sn and Hn0 on the Stanley-Reisner ring of the Boolean algebra. For Sn, the definition is very natural. You have a multi-chain, then you just permute these numbers 1 through n in this multi-chain. That's an Sn action. Okay? There are these special elements, rank polynomials, theta 0 through theta n in the Stanley-Reisner ring, and they are fixed by Sn. They are Sn invariants, and this is a definition by example. If n is 3, theta 0 is 1, that's always true, and theta 1, theta 2, theta 3 are the sums of variables whose indexing subsets have the fixed cardinality of 1, 2, or 3. And if you transfer this, guys, you got the elementary symmetric functions in the polynomial ring. And moreover, okay, so the Sn invariance for the Stanley-Reisner ring of the Boolean algebra is a polynomial algebra in these thetas. It's rank polynomials. Okay, so this is analogous to the results when you consider Sn invariance in the polynomial ring. Right, you have a polynomial algebra in these EIs. It's very similar. So now we want to define Hn0 action on the Stanley-Reisner ring of the Boolean algebra, and this is an example. We have 3 cases. If you want to apply a generator of the zero-hack algebra to a monomial, it depends on you look at I and I plus 1 in this multi-chain, depends on which one appears first. You have 3 cases. Okay, and you sometimes swap them, sometimes you have a -1, sometimes you just kill this. Okay, and with this action, we can now define an ideal in the Stanley-Reisner ring which is stable under this action for any composition alpha. And so the quotient becomes a H10 module, multigraded, and is projected. So you can send this to NCM, and you should have a multivariate non-commutative function, and that function is this. And you have some of these non-commutative ribbons, and the coefficients are the products of TIs or algebrans through the descents of this composition. And you notice this is pretty similar to the definition for the non-commutative politude of Nanterbo-Giron and Mac-Zabrocki, and it's actually this, given by this identity. You specialize T sub I to T to the I power, and you recover that. Okay? And you can also recover their QT analog for any composition alpha. You just need to use the composition 11111. You have multivariate, right, T1 through Tn-1 from my result, and you specialize T sub I to T to the i's power if I is the descent of this composition alpha. Otherwise, you specialize Ti to Q to the n-i, and this gives you the QT analog. Okay, so that's half of my main result, and the other half is about the quasi-symmetric characteristic. And I'm going to skip this definition for the ideal I alpha. It's not so hard. But this is my the other half of my result. So if you consider the quasi-symmetric characteristic of this Stanley-Reisner ring of the Boolean algebra, there are a few ways to write this down. Okay, and you have these fundamental quasi-symmetric functions multiplied by certain coefficients from the statistic of in for descent. And there are a few ways. And this may not look so nice, but there is actually a way to specialize this to get something pretty interesting. So this was a result by Garcia and Gasso in 1979. They got a generating function for these 5 permutation statistics: in, match, inverse, des inverse, match, and des. And they have this nice way to write this generating function. And we can recover this result from our result on the previous slide by doing some specialization like this. Okay. So, okay, I guess I'll just stop here, and thank you very much.